Jnanam paramam dhyayam. Knowledge is supreme.
In the last lecture, we started our study of polynomials over a field, and what we saw was we use division with remainder to decide whether a given element of the field is a zero of that polynomial or not. So, let me recall briefly what we did. So, K is a field, arbitrary field, and f is a polynomial with coefficients in K, and let us assume f is non-zero. Then we have noted as a consequence of division with remainder that if I have an element A in K, then f of A is 0 if and only if the linear polynomial x minus a divides f in the polynomial ring Kx. So, we are interested in finding out, remember our main aim is in this course is to find roots or zeros of the polynomial, and this information is useful only when the roots or solutions or zeros they are in the field K. But it may happen that your polynomial may not have any zero in K. For example, if I take K equal to R and f equal to x square plus 1, then this polynomial f does not have any zero or solution or a root in the field R. So, remember henceforth I will use the words like root or zero or a solution. These are the same meaning of f, means an element A somewhere, may not be in F, may not be in K, but maybe in a bigger field than K, in some L, where L is a field which contain K and f of A is 0. Such a thing is called a root or zero or a solution of f, and one should specify in L, where L is a given bigger field. And in former days, the people, researchers, they were working in a special field, rational numbers, and definitely they knew that inside the complex numbers all polynomials have zeros. This was precisely so-called fundamental theorem of algebra, which we will also prove it, but I am gathering the information or gathering the vocabulary, and then we will start proving things, so that we will have less and less confusion. Okay, so what did we decide in the last lecture? An element in a and that given field K I will keep calling a base field. So, this K, the field we start always, that is called a base field. In former days, that was usually Q, field of rational numbers, because that is the smallest field that we got it from natural numbers. From natural numbers we got integers, and from integers we got rational numbers. That is the field, and that is the smallest field. Nowadays, because of the applications, one also considers finite field. So, in general now I will keep arbitrary, K is arbitrary base field and this Q will be the classical case, and arbitrary other fields will also be very important for the applications. So, we have proved last time, in the last lecture we have proved that every polynomial f in Kx has a factorization like this. F is non-zero and this f definitely I can factor it as, first of all, this f will have a leading coefficient. So, I want to call that A to be the leading coefficient of f. So, if I take out, because I am in a field and this A is non-zero, because f is a non-zero polynomial, this leading coefficient is non-zero. So, I can always take out, take out a common factor. That I can do it because that is amount to saying that you are multiplying by the inverse. So, that means this f I can definitely write it as A times some g, where the g is another polynomial. Now, g is monic. This I can always do it because A is non-zero. Just multiply f by A inverse and you get g. So, g is monic. And then this one we try to see whether some elements of K is a 0 of g or not, and that will be then the linear factor of g. So, this g definitely I can write it as A times product. This product is varying over C in K such that x minus C, and maybe some this x minus C may be repeated factor. So, that the multiplicities are alpha C times now the other factors. So, that will be, I will, unfortunately I can't write here, so I will write it down there. This is times product. Now, this product will run over degree P bigger equal to 2 and P power alpha P, where only finitely many factors occur here. This product is finitely many, that is only finitely many linear factors are there. These are the multiplicities. Similarly, these P are prime polynomials. In Kx. Remember, prime polynomials in Kx means, this is we defined last time. So, it means two things. First of all, P is monic, and the only divisors of P in Kx are either the only divisors of P are of the form some B times P, where this B is actually a unit in K, that means it is in K cross. That is the only divisors in Kx. So, these are also, some books you will see, these are also called irreducible polynomials. But when an irreducible polynomial is monic, I call it a prime polynomial because they are analog of the prime numbers. So, prime numbers are the one which don't have divisors other than 1 and itself in natural numbers. So, the same philosophy. So, therefore, we have written now immediately from this, because we are over a field, when you compare the degrees on both sides, we will get the formula that if I take all these alphas, so that is summation alpha C, C varies in that K, and only finitely many C, this sum is only finitely many, plus the degree of P, where P varies in that product, P degree P bigger equal to 2 and prime polynomial. This degree is on the degree of the right side. See, this degree is, I am comparing the degrees. So, this doesn't fit in one line. This degree here is the degree of this. The degree of this is, for each factor it is this. So it is a sum. Similarly here it is a sum alpha p and the other side is degree f. So this is equal to degree f. This is the degree formula. Because we are over a field, so the sum of the degrees of the factors in the product equal to degree of the product. That is what we are used for this. So in particular, what did you inform? In particular, we have proved that the summation alpha c in k, this is less equal to degree f. And when can equality hold here? Equality will hold here, that means when f has no factor of degree 2 or more. So equality holds if and only if f has no factor of degree bigger equal to 2. No prime factor, I should write. So that means this part is absent, right? Actually this was for a long time. So in particular, so now let me, before I write down further in particular case, let me introduce a notation here now. So this we will use it throughout the course. This is very, very important. So suppose I have a field K and I have a bigger field L. So this one means that the operations are same. That means the addition and multiplication in K is induced from the addition and multiplication in L. In particular, the 0 element in K, 0 element in L are same. 1 in K and 1 in L is same thing, that is assumed. So such a thing I will call a field extension. Field extension. These are fields and one is contained in the other, or this is K is a subfield of L or L is a bigger field than K. Now, and if I have a polynomial f given in with coefficients in K, then I will write here V suffix L of f. This means all elements x in small x in capital L here such that f of x is 0. That means small x, so this is also, one can say this is the solutions of f equal to 0 in L, right. So, and this is what we want to study, and whether our main problem is, can you find, given a polynomial f, can you find L so that all the solutions are in L, and whether the solutions have closed formulas in terms of the coefficients of f. That means using addition, multiplication, subtraction, division and extracting the square root. That is the problem of the Galois theory. This Galois theory centers around studying this problem. So this is, and what we proved above is the cardinality of V, K, F is less equal to degree of f. This is what we studied. This is what follows from that. In fact, a little bit more. What more? That each element in VKF we attach a multiplicity, and not only the distinct points, but if you count each point with the corresponding multiplicity, then also the sum is less equal to degree. Actually, this was proved by, I wanted to make that comment, this was proved by Vite. I will write here in the bracket. This is very important observation. This was, for a long time people didn't know. So this is Vite. The French mathematician who lived between 1540 to 1603. and he has observed this around 1591. Actually, the notation about capital X to denote capital X the variable in a polynomial, also this polynomial ring, that notation is also due to Witte. And in fact, he has written a book. Okay, so the book I just mentioned it, it's interesting. It is called Introduction to Analytic Art. This is Witte. He also gave methods to solve degree 4 equations in a trigonometric way. Anyway, so this was, you see, those days the language was not English, the language was Latin, and in that this title I have translated in English, but in Latin it is in Artem Analyticum ISO Goge. This was what the title was. So there you will find this theorem. So let me state now what we proved, what this observation as a theorem, so that we can refer. So this is theorem, this is Witte. A polynomial f with coefficients in a field kx of degree n, where n is natural number. Remember, this assumption means that f is non-zero, because once you say a polynomial of degree n, that means f cannot be 0. We have defined degree only for non-zero polynomials, and degree can be 0. Constant polynomial have precisely degree 0. So a polynomial of degree n has at most n zeros in K, even if these zeros are counted with multiplicities. This is what we have proved is well. So that is summation of alpha c is less equal to the degree f. Very important. So we know there cannot be more. But this also shows not all can be in the base field, or none can be also. So for example, I gave example x square plus 1, that over real numbers it has no 0. Degree is 2, but it has no real 0. Similarly, if I take polynomial x power n, for example, minus say p, where p is a prime number, think of this as a polynomial in qx. The degree is n and it has no 0. This is f. F has v. Better to use this notation again and again, so we will get fixed. V q f is empty set. And our problem is to find v all zeros. That means you enlarge q to c, for example. C may be too big, you may not need whole big C. So enlarge Q to a big field so that all zeros of f are there, and then say how do you write the formulas, or is it possible to write formulas? So that is the problem. Okay, so these polynomials, actually this polynomial f is a prime polynomial, f is prime polynomial in Qx. This is not immediately trivial. But this we will prove it later, but right now we only want to say that there is no 0. So that is easier to prove. If so, let me just indicate this proof. Suppose x is a rational number and suppose f of x is 0. I should get a contradiction because this is empty set. So x is a rational number, so x will be of the form a by b, where a, b are integers and b is non-zero. So any rational number by definition is like that. And then I want to check that this cannot, so I want to check that f of ab cannot be 0. So if f of ab is 0, a by b is 0, not ab, a by b is 0, that is equivalent to saying when I plug capital X equal to a by b, then it becomes 0. So a by b power n minus equal to p. P is a prime number, but that equation is equivalent to saying a power n equal to p times b power n. Okay, to start with, I could have written this fraction as the lowest fraction. That means these integers a and b have GCD 1. That you can always do it because if they have a common factor up and down, you cancel it. And then this is usual trick what we have been learning in the school for so many years. So GCD is 1. So that means a and b doesn't have any common factor. In particular, they don't even have a common prime factor. So, but you see, this p divides the right hand side. So therefore p will divide a, but a power n, but p is a prime number. So if p divides a power n, then p will divide a. But once p divides a, p power n is a factor here, and you cancel one of the factor, and then the remaining n minus 1. So you need a condition n is at least 2. So this is not possible. Clear, no? Because if p divides a power n, then p divides a, then this will divide, the left hand side will be divisible by p power n, but then you cancel one p, but p power n minus 1 still divide the left hand side, which is at least 1. So p will divide b power n, and therefore p will divide b, and therefore GCD cannot be 1. So therefore what altogether we have checked that? We have checked that V Q F is an empty set. So there is no 0. So how do we find and where? So that problem we are doing that. Okay. So now let me give one more application of that theorem of Vita. So for example, now I want to apply these to the polynomial. I take first of all k to be z mod p. P is a prime number, and I take the field z mod p. This is this field we have got it from integers by defining a congruence relation there, and then taking the congruence classes and defining addition and multiplication there, and it became a field. This field, and I am going to take the polynomial x power p minus 1 minus 1. This is a polynomial with z mod px. This is a polynomial with coefficients in z mod p. So one should really write this one as 1 bar. Okay, and then what do we want to apply? What did we write? We want to find out, first of all, note that x power p minus 1 minus this polynomial, this given polynomial is in fact the product is varying from k equal to 1 to p minus 1. There can't be more because the degree is p minus 1 and x minus k. And strictly speaking, I should write k bar. this is, I want to check this equality first. So what do I have to check? I have to check that when I expand this side, only two terms remain, the degree term and the constant term. So in between terms become 0. Or I will have to check that this is, I just want to say that this is precisely what is known as Fermat's little theorem. What do you have to check? That each one of them is a factor here. If I check that, that is enough. Because if each one is a factor here, therefore they are different factors, they are different prime polynomials, and therefore they will divide, all of them will divide this. Therefore this product will divide this. But on the other hand, there can't be any more, because this degree is p minus 1, this is also p minus 1 degree, and both are monic. So once you prove that, to check this, enough to check that, I will write on the next page. Enough to check that for each k from 1 to p minus 1, x minus k bar divides x power p minus 1 minus 1 bar in this field, in this polynomial ring. This is what I have to check. But just now we observed in the morning, the few minutes back, that whenever you want to check somebody divide this, it's enough to check, this is enough to check that when I plug in k bar in this, it should become 0. So this is x power p minus 1 minus 1 bar, this polynomial, if I evaluate it at k bar, it should become 0. That means when I put x equal to k bar, but that is equivalent to checking k bar power p minus 1 equal to 1 bar. But you see, where is k bar? K bar is an element in Z mod p, and k bar is not 0. And this is precisely what we have called it, Z mod p cross. And Z mod p is a field. Therefore, this is precisely the group of units, and this is a group of then order p minus 1. So it's a finite group of order p minus 1, and this k bar is one element there. So when I raise that element to the power of the order of the group, you should get a trivial element in the group or identity element in the group. This group is with multiplication. So the identity element in this group is precisely 1 bar. So therefore, this follows, this equation follows. So this is also called what is called Lagrange's theorem. It follows from Lagrange's theorem in group theory, which also we will prove. So remember, just remember, we have used the fact that, so I will write in the bracket, this follows from Lagrange theorem in finite group theory, which says that if G is a group finite of order n, and G is an element in G, then G power n is identity element E in G, where this E is the neutral element in G. This also we will prove, I will indicate when I prove more general than this. But right now we accept this. That is what I mean by when I said I will assume that the participants of this course are familiar with abstract algebra first level, that means finite groups, also vector spaces, little bit of rings, little bit of fields, and linear algebra, etc., etc. So we have checked that. Coming back here, what did we prove? We proved that we have proved such an equation: x power p minus 1 minus 1 bar equal to product k in from 1 to p minus 1 x minus k bar. So now that means what? And this is in z mod p x. So that means if these polynomial factors actually into linear factors, and we know also the zeros, and we know they are precisely so in the base field. They are actually all in base field. So there is no need. Formula is clear. So now I want to deduce one more fact from this equation. Now in this equation, I am going to put, this is the equation, this side is polynomial, this side is polynomial. So I can arbitrarily put x equal to whatever values I like in this. So put x equal to 0 on both sides. And what do we get? We get here minus 1 bar, because x is 0 I am putting, equal to x is 0 I am putting. So this will be minus sign how many times? P minus 1 times, and the product of this. So what do we get? Minus 1, I will take that out, minus 1 power p minus 1 times 1 bar, 2 bar, etc., etc., up to p minus 1 bar. Right? But then this is equation in z mod p. Now I want to write the equation in z. So there are two numbers, they are equal in z mod p, means they are modulo p, they are equal. That means, so this minus 1, so I want to lift this equation to z. So minus 1 is congruent to, and you see p is a prime number, therefore p minus 1 is even. So therefore minus 1 power, that is just 1, and then instead of bars I have to write, so 1 into 2 into up to p minus 1 mod p. That is the meaning of the above equation. But this means minus 1 is congruent to p minus 1 factorial mod p. This will remind you theorem which you might have proved in your college days. This is called Wilson's formula. Okay, so we will continue after the break our study of polynomials and the zeros, etc. Thank you.